We were talking about the what are called the simple gas laws, and now we're going to talk about what's known as the ideal gas law. We can combine those simple relationships into a single law that accounts for all of them. So the volume of a gas is proportional to 1 over the pressure. The volume is proportional to the temperature, and the volume is proportional to the amount of gas. So that tells us that the volume of a gas is proportional to NT over P. That's combining these 3 different proportionalities. If we throw a constant in there, we can change the proportionality to an equals. So volume equals N times a constant R times T over P. We multiply both sides by P, and we get PV equals nRT. And that is the ideal gas law. Sometimes students call it PIVNERT to help them remember it. And R in that equation is known as the ideal gas constant. The ideal gas constant will have different values depending on what units you use for pressure and volume. The temperature always has to be in Kelvin, so that's not an option. We often use atmospheres for pressure and liters for volume in chemistry. In other sciences, they may use different units, or in different applications, they may use different units. So the one that we need to remember is R equals 0.08206 liter atmospheres per mole Kelvin. And the units seem a bit awkward, but the units are because of all these other variables in the equation. If you rearrange that for R, you find that R equals PV over NT. Pressure in atmospheres, volume in liters, that's where that comes from. On the bottom, moles in Kelvin. So 0.08206 liter atmospheres per mole Kelvin. This is showing the relationship between the ideal gas law and Boyle's law, Charles' law, and Avogadro's law. What I'd like to show you, we'll just throw in a slide here. Whiteboard. There we go. What I'd like to show you is that you can get any of those simple gas laws from the ideal gas law. And this can save you some memorization time. So PV equals nRT. If I take that equation and divide, well, I'm going to give these subscripts. Conditions 1. I'm not going to put a subscript on R because it's a constant. It doesn't change. If I divide this by P2V2 on both sides, is it still an equality? Is it still equal? Yes, it is. And what if I substitute in for P2V2 N2RT2? Does P2V2 equal N2RT2? R2D2C3PO, right? This is the ideal gas law with different subscripts. And the subscripts are just talking about different conditions. If you change the pressure, the volume, the number of moles, etc. So that's equal to N1 RT1 over N2 RT2. Is everybody okay with that? I took the ideal gas law at one set of conditions and divided it by the ideal gas law under another set of conditions. Now, what if we just had pressure and volume changing and the number of moles of gas stayed the same and the temperature stayed the same? If the number of moles of gas stays the same, then N1 is equal to N2, right? And so those cancel out. The R's are going to cancel out because R is always the same. It's a constant. If the temperature is the same, then T1 and T2 are equal, and they cancel out. And what is this side equal to? 1. Anything divided by itself is 1. So there I've got P1V1 over P2V2 equals 1. Well, I could rearrange that. P1V1 equals P2V2. Does that look like one of those simple gas laws? So what I do, instead of trying to remember all those simple gas laws, is I just do the ideal gas law under one set of conditions divided by the ideal gas law under another set of conditions. And then I look to see what is not changing. And whatever is not changing cancels out. The R's always cancel out. And so you can develop all of the simple gas laws. There's another one we didn't talk about called Gay-Lussac's law. And then there's the combined gas law, which has 3 variables changing. You can get all of those from PV equals nRT. Or you can memorize all the individual ones. Let's see. Make sure I didn't skip it. Okay. Let's do an example with the ideal gas law. So an 8.50 liter tire contains 0.552 moles of gas at a temperature of 305 Kelvin. What is the pressure in atmospheres and psi of the gas in the tire? So students vary in their ability to interpret word problems. If you're on the higher end, you'll look at that and recognize that nothing is changing here. We don't have the gas being cooled or things expanding. We've just got one set of conditions, and that tells us we're going to need the ideal gas law. If you're on the lower end of interpreting word problems and that's not obvious to you, you can still take the same approach of making a table. What you'll find is that when you make the table, there's only one row. So I'll show you how to do that, and then we'll do it the other way on another problem. So let's pretend that we're just not really sure what's going on. It's early in the morning and we're tired. So this is a gas law problem, and we're going to make a table like we were making for the simple gas laws. We got 1 and 2, and then I'm just going to write down the numbers as I come to them in the problem. An 8-liter tire. So I will write down 8.00 liters. And I ask myself, well, liter is a unit of what? It's a unit of volume. And then the next number is 0.552 moles. Okay, I'll write that down. 0.552 moles. Well, in gas laws, what letter do we use for amount of gas in moles? N. And then it tells us the temperature is 305 Kelvin. Well, that was kind. They're not making us convert from Celsius to Kelvin. And then the question is, what is the pressure? So there must be a pressure column here. And that's the question. We're out of numbers. There's only one row. That's okay. Making the table wasn't a waste of time. I'm going to erase the bottom of it. But now I have all of my numbers labeled. Yes. Thank you. My eyes are a little bleary. It's 8.5. Actually, my eyes are a little old is the problem. Okay. So here's P. P is what we're solving for. Everybody okay with that? Nothing's changing. We're going to use the ideal gas law. PV equals nRT. So PV equals nRT. We're trying to find the pressure, so we rearrange this by dividing by volume on both sides. P equals nRT over V. nRT over V. So now we plug the numbers in, including the units. N is 0.552. Okay, I'm not going to have enough room there. I'm going to do this down here. 0.552 moles. And then R. Well, if you don't remember it yet, look it up. It's 0.08206. And the units are liters, atmospheres over mole, Kelvin. And then that's times the temperature, 305 Kelvin. And the whole thing is divided by the volume, which is 8.50 liters. You want to stick all the units in there because you should always double check that your units are doing what you think they're doing. Mole cancels mole, liter cancels liter, Kelvin cancels Kelvin. I'm left with the unit of atmospheres, which is an appropriate unit for pressure. So then I use my calculator, 0.552 times 0.08206 times 305 divided by 8.5. So the pressure is 1.62537 atmospheres. I didn't want to write down all the digits, but I wanted to write down some extra ones because we're supposed to also give this answer in PSI. So how should I round the answer in atmospheres? 3 sig figs, right? I've got 3 here and 4 there. That's not an exact number. And 3 and 3. So one of my answers is 1.63 atmospheres. That's the pressure in atmospheres. And then it also wants the pressure in PSI. So I'm going to take that pressure, 2537 atmospheres. And I'm going to multiply by the relationship between PSI and atmospheres. 14.7 to 1. I have the whole number still in my calculator, the full thing, so times 14.7. And the pressure in PSI would also have 3 significant figures, and that's going to be 23.9 PSI. Any questions? Let's do another one. What volume of gas, what volume does 0.556 moles of gas occupy at a pressure of 715 millimeters of mercury and a temperature of 58 degrees Celsius? So this time, instead of making the table, which I still could do, I'm just going to write things down and label them. Different approach. 0.556 moles. Well, I can tell from the unit that that's N. The pressure is 715 millimeters of mercury, and the temperature is 58 degrees Celsius. When you see degrees Celsius in a gas problem, a red flag should go up, a bell should go off, something should happen, and you should say, oh, I need to convert that to Kelvin. Let's do that right now. Plus 273.15 331.15. And the uncertainty is in the ones place there. So I'm trying to find the volume. I'm going to use PV equals nRT. Oh, I don't want to put it there, though. I'm going to need that space. PV equals nRT. This time I'm solving for volume. So the volume is going to equal nRT divided by P. So N is 0.556 moles. The ideal gas constant is 0.08206.
Okay.
Yes?
You need to convert the P into atmospheres?
I do need to convert pressure into atmospheres. Because as I'm writing the units on the ideal gas constant, I realize, oh, wait a minute. Atmospheres and millimeters of mercury aren't going to cancel out, are they? And if you don't recognize that at this point, when you go to cross the units out, you will. So I left some space up here so that I could fix that. 1 atmosphere is exactly equal to 760 millimeters of mercury. So 715 divided by 760, 0.940789. That actually has 3 sig figs. I want to carry 2 or 3 extras, though, to avoid rounding errors. And again, I've written too large. I'm either writing too large or too small. I'm just going to start over down here. Just writing the same thing a little smaller. And so I have room to put the pressure in. 0.940.
Shouldn't that be the temperature?
Thank you. Yes. I did that on purpose. No, I didn't. Thank you. 331.15 Kelvin. Divided by the pressure, 0.940789. This bottom line here, this is what I would consider the minimum of showing your work. And the reason you want to show your work is because you can look back and see what you've done. You can see if you didn't get the units to cancel out. You could see if you put the pressure and the temperature in the wrong place. You know, you're doing a mastering chemistry problem and it says, incorrect. Well, if you haven't shown any work on a piece of paper somewhere, then you start over and try to figure out what you did wrong. If you showed your work, you can go back and look at it. And sometimes it's as simple as, I wrote everything down correctly and I put it into my calculator wrong. 0.556 times 0.08206 times 331, it's not a 1. 331.15 divided by 0.9400789. I'm coming up with a volume. This would have 3 sig figs of 16.1 liters. Volume equals 16.1 liters. The moles cancel, the atmospheres cancel, and the kelvins cancel. Any questions?